Hello friends, today we are going to learn about circles, tangents to a circle, part 2.
Hello viewers, you are welcome back to this series of programs on mathematics for class 10. We are dealing with the sub-series on circles, and so far we have given you 3 programs. Now before we take up the concepts that we want to get across to you in the 4th program, let's quickly review what we did in the last 3 programs. The results that we brought to you in the last 3 programs are: number 1, equal arcs of the same circle or of equal circles cut off, number 1, equal chords, and secondly, they make equal central angles. Next was equal central angles cut off equal chords and also equal arcs from the same circle or equal circles. Then perpendicular from the center bisects the chord and the corresponding arc. And then we had that if you have a line joining the midpoint of a chord to the center of the circle, then this line is going to be perpendicular to the chord. This was followed by the equal chords of a circle or those of equal circles are equidistant from the center. And conversely, we had told you that the chords which are equidistant, they must be equal. Then central angle that is subtended by an arc is double the angle that the same arc subtends on the circle. This was followed by a corollary, a result which follows from this result, that is, the angle in a semicircle is a right angle. And then we had that in case an arc subtends angles on the remaining part of the circle, then these angles are equal. And in the last program, we had given you that opposite angles of a quadrilateral are supplementary. And thereafter, we gave you a result whereby we showed you that in case you have a situation like this, where you have got from an outer point outside the circle a tangent and a secant, then the product of these two segments of the secant is equal to the square of the length of the tangent. After this, now we are ready for going into our present program. Now in this, we have been so far seen that we have been talking about the secants, the tangents, the chords. We take in particular the situation where we talk about a tangent and in relation to that tangent a chord. So let's first draw a circle. In this circle, we want to have, this was the center of the circle, let's call it O. What would you call this line that I am drawing here? This line AB is having just one point in common with the circle, so we call such a line the tangent to this circle. And from this common point, supposing I draw this part of the line here, what would be termed this? Let this be common point P and we call it Q. This is a chord. Now in case I take any other point here on the circle and join it like this and join it like this, then I am having an angle made on the circle by this chord PQ or this arc PQ. Now this angle we want to explore as to what relation will this angle have with the angles here or this one. Now in case we join this P to the center like this. Then the point that we are getting here, let us call it R. Let this point be C. Now, in case I join this R to this Q, now recall a theorem, a result that we give you earlier. What relation will these two angles have? Surely, these are the angles which are subtended by the same arc on the remaining part of the circle. So, these two angles are equal. For simplicity, I will just say that this angle C is equal to angle R. All right. This point P was joined to the center and then produced on. In that case, what would you say this angle is? This is the angle between the radius and the tangent. So, this has got to be a right angle. This angle is a right angle. All right. Now, POR, what is this? This is one of the diameters of the circle. This diameter splits the circle into two semicircles. What would you say this angle is in that case? Angle in a semicircle, which is again a right angle. Now, we got a right angle here, we got a right angle here. We got these two angles equal. Now, if this angle is equal to this angle, then what would you say this angle is? This angle RPQ, can I say this is 90 degrees minus angle R? Because this is 90. In this triangle, these two angles together have got to be 90 degrees. Well, can I write this as 90 degrees minus angle C? This is R C. So, I have just replaced R with C. Okay. R P Q is 90 minus C. Then what will be this angle? See, R P Q is only this. From here up till this is 90. If this is 90 minus C, then what can you say about this angle? This angle has got to be this. Means this angle has got to be C. Because 90 minus C gives you this angle RPQ, this one, and if this we subtract from 90, we get this, or you can say that 90 minus 90 minus angle C gives you angle C. That is the result. We see here that in case a tangent is touching a circle, at the point of contact, a tangent has got to touch a circle, yes, and from the point of contact of that tangent and the circle, we draw a chord. Then the angle subtended by this chord in the remaining part of the circle, we call it alternate segment, which is on the other side. The alternate segment, that angle is equal to the angle between the chord and the tangent. What does that mean? Let us look back at the figure again. Now, in this figure, you have got this chord PQ making this angle, we found it equal to C. What would you say about the angle QPA? To understand this, let us draw the figure once again. We take this figure, again a circle. This was the center. We draw the tangent. As we drew last time, and from this point of contact we had drawn this chord. This was A, this is P, B, we call this as P, and we call this as Q. Now, this angle we found is equal to this angle. these two angles we have just seen are equal. Now, what can we say about this angle? This angle APQ can I say that this is 180 minus angle QPB? Because this angle whole is 180, this is 180 minus this angle. And we had a result in the last program where we saw that in case there is a cyclic quadrilateral, that is, I complete this quadrilateral now and have this vertex of the fourth vertex of the quadrilateral here. This point we had called R, let us call it S. This angle plus this angle are 180, they are supplementary. This is what we saw in the last program. Also, APQ is 180 minus QPB, that means these angles are also supplementary. So, that means that angle APQ, I write angle APQ is equal to angle PSQ. Because for this angle the alternate segment is on the other side, because alternate means if this is a chord on this side, alternate segment on this side, this chord angle on this side, alternate segment will be on the other side. So, this is a very important result that we derive from here, that in case a chord is drawn from the point of contact of a circle and a tangent, then the angle that this chord subtends with the tangent, these angles are equal to angles in the alternate segments of the circle. Now, having talked about the chords, the secants, the tangents, you remember in one of the last programs we had shown you how to go about drawing a tangent. We had shown you this process whereby we took a point on the circle, draw a perpendicular, right angle, and then we got a tangent. Then also we discovered that in case you have got a point outside the circle, then we got two tangents, PA and PB. Well, we had talked about two tangents, we had talked about a tangent on a circle. We are now getting on to a position whereby we partly recall one of the earlier results, where we had three non-collinear points and we drew a circle passing through these 3 points. But the situation slightly we are changing here. We take up a triangle. Now, in case I am given a triangle, as I draw any triangle here, in this triangle, can I draw a circle which is passing through A, B and C? For drawing a circle which is passing through A, B and C, I need a point somewhere here which is equidistant from A, B and C. For that purpose, we draw the bisectors of any two sides. To bisect this side, this is what you do. Draw the bisector. And we get this line, and then draw the bisector of any other side, either this or this. Let us have this one. And we get the bisector. all we are interested in is where these two bisectors are intersecting, that means the common point to the two. This is the point. Now, in case I take this point as the center and open the compass up to any vertex and draw the circle, this circle is going to pass through all the 3 points. This is how we can draw a circle which is circumscribing, going outside a triangle. Now, we relate this with another situation which is based on our result that we just proved. Now, supposing I take up this side of the triangle and parallel to this side I draw a tangent here. This is a tangent which is parallel to this side. Now, if this tangent is parallel to this side, what can you say about this angle and this angle? This angle is going to be equal to angle in the alternate segment, means this angle. These two angles will be equal. This one, this angle is going to be equal to the angle subtended by this, that means this is equal to this. Now, in case it so happens that these two angles are equal, then these two will also be equal. And if these two angles are equal, then in that case what can you say about these two sides? They are equal. Means we have to explore another situation, that is, in case I take a circle and from a point of that circle I take two chords which are equal in length, then if I draw a tangent from the common point of these two tangent chords, then what will happen to the third side? Let us explore that. Once again we consider a circle. See, this is a circle. Let me mark the center of this circle here. And now we take two chords which are of the same length. How to take those two chords? Simple. I mark here, that is from here up till that point. This is one chord. Then I take another chord. These two chords of this circle are of the same length. These two chords we have taken as, say, AB and AC, which are equal in length. Now, in case I draw a tangent at this point, what will I do? I will be joining O to A and then drawing a perpendicular. I have to join it here, and then we saw in the very first case where we showed you how to find out how to draw the tangent to a circle. You make a right angle, like this, and then to get the right angle here, we get this point which is going to give us a right angle, and I draw this tangent. Now, if I draw this tangent like this and also I join these 2 points B and C, what can you say about this line, this tangent and this chord, the third side of this triangle? You can verify this and this, say this one here and this one here, they are going to be parallel. The simple reason being that these chords are equal, so these angles are equal. If these angles are equal, that means these angles are equal. So, these two angles equal, this angle you know is equal to angle in the alternate segment, means this angle and this angle are equal, and this angle is equal to this angle, because in a triangle you have got two sides equal, so the base angles have got to be equal. So, this angle equal to this, meaning thereby that this line has got to be parallel to this line, alternate angles being equal. This is just one application of this result. There are many more, but now we want to switch over to a situation where we are not talking about one circle, two tangents, or one tangent or chords. We want to go on to a pair of circles. Now, on a plane, what do you think the position of the circles with respect to each other can be? Let us explore these various positions. So, for that purpose, we take a circle here. If we want to draw another circle in relation to this circle, the second circle can be like this, or it can be outside like this. These are concentric circles, means having the same center. But in case I take a circle again, say this one, and I draw another circle like this, this is another circle. These two circles are such that they are having 2 points in common. These are called intersecting circles. There are more positions of with respect to the circles. We need to introduce ourselves to various positions before we start dealing with these. With this as center, I can have a circle like this. And then I can be having a circle which is drawn with a specific aim, that is on this line. I take a measured distance and then take this as the center, any distance, then I draw a circle. Now, these two circles are such that they are having a common point. They are touching circles, but one circle is inside the other, so we say internally touching. Similarly, you could have a circle which is touching this circle externally. For that, supposing from this center, I take this point outside and then measure the distance from here to this and draw this circle. These two circles, now this circle and this circle, they are externally touching or externally tangent to each other. With respect to these circles, we want to see now a situation where we can have the tangents drawn which are common to the two circles. So, first of all, we take a situation where we have two touching circles. So, I draw a circle, this one, and another circle which is touching this circle. So, for that purpose, this is going to be the line of their centers, a circle with center O, and let us call it P, and another circle with center P, but touching the first one, taking this length, we draw this circle. Now, these are two touching circles. We want to draw their common tangent. One of the common tangents is obvious, because this can go from this point. What is the property of the tangent? When we talked about the tangent and the radii, then we said that the tangent, if from the point of contact of the tangent and the circle, we draw a radius, then the angle between the radius and the tangent is always 90 degrees. So, same thing here. In case I want to have a tangent from here, then I have to draw a perpendicular to this line OP passing through this point, let us call it A. From this point A, if I can draw a line which is perpendicular to this OP, then that is the common tangent. So, you draw the perpendicular. This is what you do to draw the perpendicular. Take this point, and then after that you draw this arc and draw this arc, and this is what we are looking for as the common tangent to the two circles. Let us call it, say, C and D. I put these arrows to show that this is a line which can be extended. But now the question arises, is this the only tangent which is common to the two circles? No. Just have a careful look. You could be having a tangent which goes like this. You could be having a tangent which goes like this. One of these tangents. How to draw these? Now, before we come back to this touching circles and draw these two tangents, we start by having two non-touching circles, because that will explain the process better, and then come back to this. So, we take two circles which are not touching. This is one circle, and we take the second circle, and this second circle is having its center here, and naturally you will have to draw the line of centers. From the line of centers, in case we want to have the tangents which are going like this, then for that purpose you take the difference of these two radii, means you take this and take the difference up to this. With this difference as the radii, now you draw a circle. And next thing, you draw a circle which is passing through this point and this point as diameter. So, draw the bisector. And this gives us the bisector of the two. This point as radius, center. You draw a circle. You don't need to have the whole circle, you may or you may not. All that we are interested in is that this point where it is cutting this circle and this point, this is because we are going to get onto a situation that now this circle, in case I join this point here to this point, this is going to give me a right angle. Can you reason why? This is going to be a right angle. The reason is that I have this as a semicircle and this is the diameter of this circle. Angle in a semicircle is a right angle. The moment I join this here and go on, and then in case I get from here a line which is parallel to this line here, joining these 2 points, you get the direct common tangent. Similar process goes on to